Today we're going to learn about well-posed, non-trivial engineering design optimization problems. We're going to first revisit a few of the concepts that we learned in the first lecture regarding problem formulation decision space and also the problem formulation cycle for engineering design optimization. Then we're going to learn about concepts including feasibility, constraint activity, and monotonicity. These are important in understanding formulation analysis and the overall formulation decision space and the problem formulation cycle. Finally, we're going to go through an example problem. This is an engineering design optimization problem that involves a structural rod, and it's a nice simple problem that gives an example of what we call a non-trivial problem formulation. Let's start off talking about the engineering design optimization problem formulation decision space. Let's think first about how the skill of problem formulation for engineering design optimization problems is traditionally acquired. Really, it's through experience and trial and error. At least this is my experience. When I first learned about design optimization, I gained some initial skills, and I went to graduate school to learn more about design optimization, and I worked on a lot of different projects. Some were academic projects, many were industrial projects, and over the years I gained knowledge about how to make decisions about problem formulation that tended to help me be successful. Here I'm going to attempt to accelerate the learning process using a systematic framework that I call the Engineering Design Optimization Problem Formulation Cycle. This is actually a design thinking principle. One of the core elements of design thinking is the concept of iterating between problem formulation and problem solution. And as we learn things from each part of this cycle, we can iteratively improve each element. Let's think about the elements of engineering design optimization problem formulation. There are three main areas where we need to make decisions, including how do we represent designs in a way that allows us to formally distinguish between designs and also manipulate these designs using some type of design automation method. So, for example, optimization. Comparison metric definition. We need to rank the designs. How can we objectively say whether one design is better than the other? And then finally, we need some type of predictive modeling tool that allows us to take a design that's specified using our design representation and maps that design to the comparison metric values. And this is where engineering analysis comes into play. The composition of all three sets of decision types forms what I call the engineering design optimization formulation decision space. Here's one way of visualizing it, where each element of the problem formulation decision space has some trade-offs. For example, let's look at design representation. We can make different decisions about how much detail to include in the design representation. At the extreme simple end of the spectrum, maybe we're only tuning a couple of continuous variables. We want to adjust these and see how we can optimize the design based on these few continuous variables. But as we move to the left toward the origin, this represents increasing the sophistication of the design representation. Maybe we add many more continuous optimization variables, or maybe we start to even bring in some discrete design decisions, things like configuration. What component should we have in the system? What should the relationships be between the components in the system? And as we move farther to the left, we get into this realm of abstract ideal design representations where the limit is, at least represented here, the ultimate in control over the design. And this may not be even definable, but if we can think at the finest possible scale that we can control the design of something we're wanting to make, that's what the origin represents. Then if we look at comparison metrics, we have many different decisions along this dimension. A comparison metric allows us to rank whether one design is better than another. For example, if we are working at a for-profit company, it would be desirable, it would be preferable to choose a design that will make more profit for the company. But that's from a limited perspective, and if we think more broadly, if we expand our scope and go beyond just what the preferences of the company might be, and think about even more broadly the good of society, maybe that represents getting closer and closer to the perfect objective function. There are some interesting problems as we start to consider more than one decision maker, as we think about how to compare whether one design is better than another. And in practice for design optimization, here we need to make the assumption that it is possible to objectively say whether one design is better than another. And that typically requires that we move out along this axis, this comparison metric axis, and we choose some kind of objective function that approximates what the overall design goal is, and it needs to be something that we can actually predict, something that we can compute. So maybe it's some kind of typical engineering performance metric, dynamic performance, mass, cost, lots of different things could come into play here. These could be either objective functions or constraint functions. And as we move even farther out, this gets into the realm of very simplified problems where maybe we want to solve an easier optimization problem, and we define a simpler and easier to compute comparison metric to get started with. Maybe we solve a simple problem early on to get some insights and then use those insights to refine the formulation. The third axis here involves predictive modeling. How do we take a design in the design representation space and map that design to values in the comparison metric space? We need some way of predicting the performance or behavior of a particular design. This is where engineering analysis tools come into play. Maybe we use something like physical experimentation. We can use a physical prototype to predict what the behavior is going to be. That's going to be expensive and time-consuming for many systems, and we'd like to speed up this process or even automate this process. In that case, maybe we move to some kind of computer simulation, and as we vary the level of the computer simulation, that's going to move us to different places on this vertical axis. There are also even more simplified models that we can go to, maybe that are represented using algebraic relationships or maybe simple differential equations. And those things, those types of models are farther away from the origin. But as we make decisions in this combined space, there are different motivations for doing so. We maybe want to define a formulation that's close to the origin to really push our assumptions and determine what is it that we really want to get out of this design. And then the next step might be to take a big step out and try to find the simplest, meaningful design optimization formulation just to get started. And then after we solve that and we learn something through that formulation and solution process, we start to move closer in. We change our formulation definition with insights we get from solution and formulation analysis, and then we try to solve again. Just a note here, this is an image from one of my research presentations. It compares two particular classes of algorithms for material distribution topology optimization. This is an advanced topic that you can take a course on later on if you're interested. But this compares the fundamental difference between these two classes of algorithms. Essentially, we're allowing some improved accuracy in some dimensions, but we are giving up some accuracy in other dimensions by moving from one class of design methods to another. This origin is sometimes referred to as the substantive rationality solution. This ideal, probably unattainable, perfect formulation. This problem formulation decision space is our basis for understanding, making, and analyzing formulation design decisions and trade-off. It's important to keep in mind that when I talk about the formulation decision space, this is distinct from the design space. When we're talking about the design representation, that's just one of the axes. And how we define the design space is one of these three major decisions. Where we are in this formulation decision space is a much more abstract concept than thinking about navigating through the design space itself. This concept of the formulation decision space, this is a foundation for a core learning objective in this class. I want to help everyone learn a systematic approach to the creation, refinement, and application of useful engineering design optimization problem formulations. In engineering design optimization, we work to translate an engineering design problem into a formal mathematical optimization problem, and then solve it using numerical optimization algorithms. In this class, we are using continuous constrained optimization as a model for engineering design problems. We can think of this formulation as a model for a design problem, or in other words, this is a decision problem. A design problem is a decision problem. This is quite distinct from an engineering system model, where an engineering system model is one that is capable of modeling or predicting the behavior of a system given a design. Rather, a model of a design problem models the decisions that we should make to achieve our design goals. Because we're using this term model, this implies that we are making an approximation. And this is true. We are making simplifying assumptions as we formulate a design optimization problem. It's important to keep in mind that solutions are optimal only with respect to the design model. That is, the optimization formulation. Moving through the problem formulation decision space changes how well the engineering design optimization problem models the original engineering design problem. And this is a concept I like to think of as formulation accuracy. If we have an accurate formulation, then it does a good job reflecting the actual design goals that we have. If we have a less accurate formulation, then it has some error in it. The solution to the optimization problem is not necessarily then going to reflect what design we should actually choose for the real engineering design problem. Let's talk about engineering design optimization as a decision support tool. Engineering design optimization provides value if the formulations are accurate enough such that the solutions can be used directly as design decisions. That's an obvious value, but this requires a high accuracy formulation. This type of high fidelity formulation could be achievable under certain conditions. We especially need design appropriate predictive models with high accuracy. This can be one of the largest investments required to pursue an engineering design optimization approach. If we already have design appropriate predictive models, then that's fantastic. Then that removes one of the biggest barriers. Often, however, the case is that we have some models that exist, but they need some modification for them to be suitable for use with design optimization. Another is that we need computable performance metrics that align with actual design goals. If we have, for example, a design goal of profit, working at a for-profit company, can we define some metrics that are actually computable, whereas an accurate prediction of profit is not going to be computable? But can we compute things that relate, say, to technical performance or cost that are going to feed in to profit? And if we can, then maybe it makes sense to use engineering design optimization as a strategy to help to support our design decisions. And of course, the profit example, that is just one of many utility functions that we could be thinking about depending on the stakeholders, depending on the goals of our design. One example of a domain that is especially amenable to engineering design optimization is either mechanical or structural design. We're thinking about Newtonian mechanics here, for example. These are systems where we can predict their behavior with a very high degree of confidence. And these types of applications were among the first where engineering design optimization, specifically for physical system design, was applied. There are other areas where models don't yet exist that are really compatible with design optimization. Maybe we have to rely on data-driven models instead of first principles models. And in that case, it can be a very intensive investment to perform a design optimization study if we are relying on data-driven models. A high-fidelity engineering design optimization formulation is one where the resulting optimal solution is an accurate approximation of what might be the actual optimal design. The resulting optimal design variable values could be used directly in final design decisions. Models and overall design optimization efforts that achieve this level of high fidelity usually require very significant investment. For example, investment in model development and computational resources as well. We have to make a case for whether this level of investment is worthwhile. And it may not always be the case that it's worthwhile, or with given modeling and computing technology, maybe it's not even possible. High fidelity formulations are not always possible due to limitations, and this is actually one of the core critiques of engineering design optimization, is that the solutions we produce may not reflect what is best in reality. We can't get a formulation that is solvable, that is close enough to reality such that the decisions could be used directly, or the resulting optimal designs could be used directly in design decisions. So then this leads us to the next question. Are low fidelity engineering design optimization problem formulations worthwhile? Let's have a look at what this might look like. In this case, the resulting optimal solution does not accurately reflect the actual optimal design. The resulting optimal design variable values should be seen as notional and should not be used directly in final design decisions. A lot less investment is required, but why go through this effort if we can't use the result in our actual design? There could be other valuable outcomes beyond producing the optimal design. For example, these activities with low fidelity optimization formulations can often reveal useful design directions or strategies. We can perform parametric studies, we can quantify trade-offs and trends that emerge from these studies. Also, design optimization can provide design insights that then can inform engineers making the actual design decisions. We might learn about new design mechanisms that can help engineers understand how best to explore the design space. Strategies for systematically moving through the problem formulation space are going to be introduced and demonstrated in later lectures. And we're going to address questions such as, where should we start? And based on what we learned through formulation and solution analysis, as well as our design goals and available resources, where should we move next in the formulation space? Let's talk briefly about the problem formulation cycle. The first step here is problem formulation. We often will perform some type of formulation analysis, and we're going to talk a little bit about that today. And if we, through this analysis, discover something that could be improved, we might iterate. There could be some iteration within the formulation step itself. Once we're happy with our formulation, then we can move on to the implementation and solution. And this could be maybe either an analytical or numerical solution. In this class, we're focusing on numerical solution, and this is often what is required for practical engineering design optimization problems. But we are going to learn about analytical solution because it's going to give us some important insights into the nature of optimization and solution algorithms. Once we have solved the problem, are we done? There's a lot more that we can learn. We can take the solution and perform analysis on it. We can perform some interpretation of the resulting optimal design and other kinds of quantitative results. There are a lot of pieces of information that are produced by an optimization algorithm that can provide some very significant insights. In addition, if we perform some type of parametric studies where we solve a whole family of optimization problems, that can give us a lot of insight into things like design trends. After we perform this solution analysis, usually it is worthwhile to go back and revisit the original problem formulation, make some adjustments and refinement, and then iterate. This is what we call the engineering design optimization problem formulation cycle, and this is really a design thinking approach to applying design optimization. Let's talk about these three concepts of feasibility, constraint activity, and monotonicity. This is all in the context of well-posed optimization problems. A problem is well posed if a solution exists. This is a fairly well-accepted definition. It does complement the definition that is given in the textbook. I'd point that out mainly to recognize that there are some differences in the definition. In other words, for a solution to exist and for an optimization problem to be well posed, this optimization problem must be both feasible, and just to be more precise, a problem is feasible if a design exists that satisfies all constraints simultaneously, and the formulation must be bounded. What do we mean by bounded? We're going to go through a few basic definitions, including things like monotonic functions, that will help us to have a precise meaning of what a bounded problem is. A problem is bounded if we reach an interior optimum. So for example, if we're thinking of a quadratic function or something else with curvature, it looks like a bowl and there's a minimum and we're not bumping up against any kind of constraints or anything. That's what we refer to as an interior optimum. So a problem is bounded if we can reach an interior optimum, or there's a constraint that we run into when we're going downhill in search of a solution. We need to watch out for problems that push design variables toward values that don't make any sense. Sometimes there are problems that could be defined that push variables to infinite values or zero values. Sometimes a zero value just doesn't make physical sense for a particular variable, or maybe negative values. An unbounded problem is something that results usually when we've overlooked something important. Maybe there's something in the design formulation that pertains to an important physical consideration and an important physical failure mode, for example. And if that's the case, if we see that we have an unbounded problem, it is most effective to really push back and question, well, what caused it to be unbounded? Instead of just putting some arbitrary bounds on the problem and proceeding that way, if we instead identify, well, what is it that we're actually overlooking that's important to the design, then we can reformulate the problem in a much more effective way. So we need to analyze the original engineering design problem and see if there's something missing. Is there a missing constraint? Or are we missing a failure mode, for example? Or something else that comes up often is, are we trying to use as an optimization variable something that is not an independent design variable, something that the engineer does not have direct control over? So for example, if we're designing the geometry of something and we're specifying some geometric specification, then that's something that's typically an independent design variable. But what about dependent variables? So things like inertia or inductance or other things that depend on the independent design variables. If we're using something like that as an optimization variable. That can lead us into trouble. That can sometimes result in either an unbounded or a degenerate problem. Degenerate meaning that it converges to values that just don't make sense. For example, going to zero, the problem is collapsing into something that just doesn't make sense. I like this quote from a textbook in 2009 where the author says, "If there is a flaw in the problem formulation, the optimization algorithm will find it." There are probably exceptions to this, but this seems to be generally true. If we have overlooked something in our problem formulation, if it results in an unbounded problem, a degenerate problem, or we overlook an important failure mode, it's going to produce a solution typically that doesn't quite make sense, or maybe it even fails. Maybe the optimization solver fails. And in that case, we really need to go back and look critically at our formulation. Sometimes with our solution attempt, that is going to provide some information that allows us to perform solution analysis. If not, then we need to go back and perform formulation analysis. Let's talk about problem feasibility. In an earlier lecture where we've talked about problem visualization, we used this analogy of finding the minimum of a function as trying to find the lowest point of a valley. We want to go downhill and see how low it can get. And then if we have a problem with constraints, we've used this analogy of a fence. If it is an equality constraint, then that means we need to stay on the fence. If it is an inequality constraint, then that means we need to stay on one side of the fence or the other. If we are wanting a feasible solution, we need to be at a point that satisfies all constraints simultaneously. So suppose if this fence was a constraint and the left-hand side here was feasible and the right-hand side here was infeasible, then the feasible domain is on the left, or any point in this domain is going to be a feasible point. With problem feasibility, we're talking about either being inside or on the fence. In thinking in terms of engineering, this means that we are meeting the engineering requirements. We're satisfying the constraints. We want to satisfy all of the nonlinear inequality and equality constraints, as well as the variable bounds. And if a point does this, then we can say the point X is in the feasible set. Let's talk about constraint activity. This deals with boundary optima. A constraint, either inequality or equality, is active if removing it from the optimization problem changes the solution. Think back to the grassy valley with the fence. If we find a constrained minimum, if we find a place where there's no more downhill direction that does not involve violating a constraint, and if we remove the fence, and then all of a sudden there exists at least one downhill direction, then that means removing the constraint changes the solution, and so therefore that constraint was active. This is a fairly nuanced way of describing the activity of a constraint. Often it means that these constraints or inequality constraints are satisfied with equality. There are some important mathematical nuances between saying a constraint is active versus saying a constraint is satisfied with equality. And in part 2 of the class, we're going to explore that in detail. One term to know at this point is the word tight. We say an inequality constraint is tight if it is satisfied with equality. It is possible for an inequality constraint to be tight, but not active. That's an important distinction, and we're going to learn exactly what the difference is later on. Also, not all equality constraints are active. When we get into the section on constrained optimization theory, we're going to go through this in detail. Here's a concept check. If we have a design vector of length n, how many constraints could be active? How many constraints could be tight? This is something that might be a challenge to answer right now, but we're going to go through the tools that you need to answer this later on. If you want to determine the activity of constraints when you are solving a problem using an algorithm such as fmin-con, some of these outputs, so especially the output struct and the lambda struct, these are going to give us information about constraint activity. This is part of solution analysis. As we go through learning about optimality theory and the numerical methods, you're going to gain the knowledge that you need to interpret the results of an optimization solution to find out things like, can I be confident in this? Or how important are different aspects of the problem? Let's talk some about monotonicity and boundedness. First, let's define monotonic functions. Just looking at Wikipedia, a function that's defined on a subset of the real numbers with real values is called monotonic if and only if it is either entirely non-increasing or entirely non-decreasing. You might be wondering, well, why are we using this term specifically non-increasing instead of just saying decreasing, or non-decreasing instead of increasing? That language allows for flat spots. Here's a figure again from, or in this case from Wikimedia, and this shows a monotonically increasing function. And here, if we have a flat spot, this function is still monotonic. It is non-decreasing, but we do have a spot where it is not increasing. Here we have a monotonically decreasing function, also with a flat spot. And then finally, here's a non-monotonic function where clearly we have downhill and uphill. We can look at the sign of the derivative of this function to determine monotonicity. How does this relate to engineering design optimization? Let's ask this question. What might happen if we try to optimize monotonic functions? Here's an example. Suppose we have a minimization problem. We have a simple positivity bound on our scalar variable x, and we want to minimize 1 over x. What does this look like? Well, this is roughly a sketch of what the inverse function looks like. And if we add our bound here, we can't go negative, and we want to minimize this problem. Is it bounded? As we adjust our value of x, what direction is that going to push us? If we try to minimize 1 over x, we're going to keep increasing x, and this is going to increase without bound. We're going to shoot off to positive infinity. This is not a bounded problem. What does this problem need to be bounded? It needs something that prevents it from going off to an infinite solution. A simple approach would be to add in a bound, and mathematically, this is going to be a bounded problem. This is an important concept. But when it comes to engineering design optimization, just simply adding a bound often is not a good strategy. It's usually the case that we've overlooked something, and so instead of adding a simple bound on a variable, it's good to find something such as a failure mode that we might have overlooked that is capable of bounding our problem. So specifically, if we add this bound, x must be less than or equal to 5, then this becomes a bounded problem. And if we think about this now in the feasible domain, x has to be greater than 0 or less than or equal to 5. We need to choose a value for x that minimizes 1 over x. It's pretty clear where the solution is. This is the smallest point in the feasible domain, or this is the value of x that gives us the smallest value of 1 over x while not violating any of the constraints. So this is a monotonic function. These are issues that we deal with when we're trying to optimize problems involving monotonic functions. And to help with this, there's a tool known as Monotonicity Analysis. There is a formal way of analyzing problems that have one or more monotonic functions, and we can answer lots of questions about these problems, including boundedness. And why is this important in engineering design optimization? Monotonic functions are super common. We have cases like, say, if we're looking at a simple tensile stress sort of model, if we're reducing the area of a member that is subjected to tensile stress, that is going to monotonically increase stress. It's going to monotonically increase deflection. And monotonicity analysis can be thought of as a tool that can be used to assess boundedness. And even if we can't assess boundedness directly on a problem using formal monotonicity analysis, it can give us a lot of important insights. So for example, if we have a problem where one or more of our functions is the output of a computer simulation, then we might not be able to apply monotonicity analysis in an exact way. But understanding the principles of monotonicity analysis can help us to do a better job formulating a problem that improves our chances of having a well-posed problem. In applying monotonicity analysis, we might be able to identify constraints that we can show are going to be active even before we solve the problem numerically. And if we can show constraints are active, we can assume that they are satisfied with equality, and then through algebraic manipulation, we can solve for different variables and perform substitution and reduce the problem size. Full monotonicity analysis is limited to problems that have analytical expressions for their objective and constraint functions. But monotonicity can provide insights into simulation-based or data-driven models as well. In this class, we're going to cover monotonicity analysis in a fairly limited way. We are going to cover it in more depth in a separate video than we are discussing it in right now. This is an important type of formulation analysis, and there are a few things that are going to be important for you to know about monotonicity as we move forward in this class. So you need to know what monotonic functions are. You need to understand how monotonic behavior can lead to problems with optimization, formulation, and solution. Also, how can you use monotonicity to simplify optimization problems? And how do you recognize when solution difficulties might be due to monotonicity issues? So for example, even if we could not perform an exact monotonicity analysis on a problem before going to numerical solution, when you go to the solution and you understand the principles behind monotonicity analysis, this could really help you have insights into what some of the potential underlying problems could be if you have some type of failure or some type of solution result that doesn't make sense. And understanding these principles also will help you in learning how to resolve these issues. Historically, monotonicity analysis has been used to actually solve problems, and this was especially useful before computational resources have increased really dramatically in the last few decades. Here, we are focusing on using monotonicity analysis for formulation analysis and also to build conceptual understanding. I'm just going to go briefly through a few technical aspects of monotonicity analysis, and then we're going to move on to the next topic quickly after that. Using this notation from one of the optional textbooks, we can say that a function is increasing with respect to x or decreasing with respect to x if its derivative with respect to x is strictly positive or negative, respectively. X is a monotonic variable if either of the above is true. And to get more precise, if we have flat spots, then we can say that this is weakly increasing or decreasing. There's a particular theorem called the Monotonicity Theorem that is an important tool for helping us to detect unboundedness. We're going to use a technique. We're going to learn a technique that's based on this theorem that will help us to systematically determine whether a problem is bounded or not. If we satisfy the conditions described here, then there's no interior optimum and there are no inequality constraints that are capable of bounding our objective function, and then that means it is an unbounded problem. As a recap, well-posed engineering design optimization problems have a solution. For a solution to exist, the problem must both be feasible and bounded. And throughout this class, we are learning the tools needed to understand both aspects of well-posed engineering design optimization problems. Now let's go through an example. We're going to look at a structural design optimization problem involving a structural rod. And this is an example of a non-trivial problem formulation. This is the type of formulation that often motivates the use of design optimization. There's some kind of non-obvious solution to an engineering design problem, and optimization really can bring some value to this activity. Non-trivial engineering design optimization problems are those where the solution is non-obvious. There are some trivial problems that could be defined where we could just look at the problem and use intuition, or just by inspection we can see what the best design is going to be. Monotonicity is often present in engineering design, and usually one or more constraints are active. And it's fine if we have active failure mode constraints, so things like stress, temperature, and so on. But if we have what might be called an active arbitrary bound, if we have something that is driving the solution of the problem, so an active constraint is something that drives the solution of the problem, and the source of that bound was a subjective human decision, then that's what I call arbitrary. And then that means the solution we're getting is not actually something that is at the physical limits of the system, but it was dictated by the human who formulated the problem. And that often indicates that there's something that we overlooked. Maybe there's a missing failure mode, maybe the model is oversimplified, or maybe we have a design representation that uses something like a dependent variable as an optimization variable. A good property of a non-trivial engineering design optimization problem is one where there's some kind of competing phenomena or other trade-offs that create some kind of non-obvious optimal result. There's some kind of sweet spot that exists, and optimization is a very helpful tool at finding sweet spots like this. An optimization-based approach is valuable if optimization formulation, modeling, and solution provide new design insights. So in addition to producing a design that could be optimal or that we could actually use, even if the resulting solution of the optimization is not something we use directly, the insights can be very valuable. It can help us get new intuition for how certain types of systems should be designed. Let's talk about this structural design example. Here we're looking at a structure where on the left-hand side we have an immovable object that our other components is anchored to. And here we have this blue rectangle that represents a rigid beam. And each of these circles are representing pin joints. So they can resist translational forces, but they cannot resist rotation. And here we are applying a large load at the end of this beam with magnitude P. And if we had just this beam and a pin joint over here, and we were pushing with P, it would just rotate. This would be a mechanism. So here we have a rod, a support rod, and it's attached here to the beam with a pin joint, and then it's attached to this immovable object with another pin joint. And because of the existence of this structural rod, it's going to prevent rotation of this beam. It's going to be pushing back. And with this force, it's going to be causing a compressive force to arise in this rod. And we're interested in designing this rod and making sure that this rod does not fail. The length of the horizontal beam is L1. The length of the support rod is L2. The vertical distance between the attachment points of the beam and the support rod is H. Here's something that is a design decision. Where should we place the attachment of the rod? Here we're denoting that as X. The vertical load is P, and here we are assuming that the rod has a solid circular cross-section with radius r. There are a number of assumptions we're making in this design problem. First, the load is specified, and it's a static load. It's a constant load. And here we're going to be ignoring dynamic behavior. The beam geometry is fixed. We're not going to be changing anything about this horizontal beam. Also, this height, h, that is fixed. The beam is rigid. That means we are assuming that it does not bend, it does not flex at all. However, we are assuming that the rod is elastic. That means we are considering how this rod deforms under load. All the joints here, here, and here are frictionless pin joints. They cannot produce any kind of torque at those joints. As designers, we are going to be choosing the rod length and the section radius. So what's the radius of this circular rod and what is its length? We can choose either L2 to be a design variable or X, but they are related to each other, and we can calculate this relationship using trig relationships. We would like to minimize the mass of the rod without the rod failing. We're going to look at some important failure mechanisms that pertain to a structural member in compression. These failure modes include yield due to axial stress, or in other words, if we are compressing the rod and there's enough internal pressure, you can think of it as internal pressure inside the rod, that it's actually going to cause the metal to plastically deform and not be able to return to its original shape. That's what we call yielding, and we're considering that to be a failure mode. Another failure mode is buckling due to compressive load. This is an elastic instability mechanism, and we're going to look at that in a little bit more depth in just a moment. This problem appears to be a very simple problem, but it turns out to be really interesting. It's quite a non-trivial design problem. There is a sweet spot in the design space that exists because we have a conflict between two different failure factors when we're reducing X, or as we adjust X, changing where the rod attaches to the beam. It has some competing things going on. If we increase X, that reduces the compressive load. Or in other words, if we push this attachment point closer out to the applied load, that's going to reduce the mechanical advantage that this load has on the rod, and so that's going to reduce the force that exists in the rod. But if we increase X, that's going to increase the length of the rod. And if you have some intuition for what happens as you compress something that's really long and skinny, like a spaghetti noodle or something, it's going to bow out, and there's a limit to how hard you can compress something that's long and skinny before it buckles, before the onset of an elastic instability. And we can calculate what this critical load is, and if we increase the length of the rod, that's going to reduce the buckling strength of the rod. So increasing X is good from a yield perspective, but bad from a buckling perspective. These two competing failure modes both depend on X, and just looking at this problem, it's not clear what the best balance is before we actually solve it. In the design optimization problem, we're going to choose the rod attachment position x. We could have also defined L instead of x as an optimization variable. And we also want to choose the rod radius r. We want to minimize the rod mass and make sure we don't have either buckling or yield failure. We have the trade-off from conflicting phenomena. Increased compressive rod force affects both yield and buckling failure modes. So this is really at the intersection of multiple things going on, and it makes this a very rich, interesting design optimization problem. We don't know which failure mode is going to be the dominant constraint in this problem ahead of time. I know a lot of students in this class do not have a background in structural or mechanical design. That's okay. I'm going to provide the formulas that you need here to follow what's going on with this design optimization problem. And in particular, pay attention to the form of these formulas. Things like what variables are in the numerator or denominator. This is going to give you a sense of things like monotonicity, or if we increase a variable, what's going to happen to a particular function? Is it going to increase or is it going to decrease? And that's the main thing that you need as we proceed through this problem to get a sense of what the conflicting trade-offs are. Here's a video of me demonstrating elastic instability in a ruler that I'm applying a compressive load to. All right, so I'm pushing on the ruler. It's starting to bow out just a little bit, but then if I give enough force, it's going to bow out and I can hold it in this deflected position. And if I were to push even harder, it would collapse. And one of the main points here is that I am pushing nowhere close to hard enough to cause yield of the metal if it was just due to the compression of the metal. But the load that produces the elastic instability, the buckling, that's much lower than would produce yield alone just through compression. So here's a little sketch describing what's going on. Say we have a vertical load and this represents the ruler or some other compression member. And as we push down, it's going to bow out if we push hard enough. As it bows out with this deflection, it has an offset, and that produces what's called an applied moment. It applies a moment, kind of like a torque, on the elastic member here. And because it's elastic, it's going to behave like a spring. It's going to be pushing back. So we have this balance between an applied moment and a restoring moment, and it behaves like a spring. So what happens if the load is really large and the applied moment is larger than the restoring moment? That means that the load is greater than the critical load and the column goes unstable and it collapses. That's what we want to avoid. That's the failure mode, this elastic instability. Long, slender columns in compression can fail at loads that are much lower than loads that produce yield. So if we have something that's long and skinny, this is something that we really should pay attention to. It's a failure mode that should not be overlooked. Here's a derivation of the critical load. I'm not going to go through this in detail, but it's based on a differential equation that models a bending beam. And if we apply boundary conditions, we can determine what is the solution to this differential equation. And we can find out, well, what is the minimum load that is going to allow us to have a stable deflected position of this compression member. So it's going to be bowed out and stable. The idea is if we go just above this critical load, then we're going to have collapse. Here's the key formula. The critical load for a column in compression with particular assumptions in place is equal to pi squared times the Young's modulus of the material, that's basically how stiff the material is, times the area moment of inertia, so that's a geometric property of the cross-section, divided by length squared. This is a really nonlinear relationship. As we increase length, we dramatically reduce the critical load. So even though in the rod problem we're only making what look like small changes to the length of the rod, it's going to have a big impact on the critical load with respect to buckling. If you'd like to go through the buckling analysis in more detail, there's a YouTube video that goes through it at length. Let's talk about some of the additional design assumptions that we're making here. The support rod is made of aluminum. It has a stiffness of 69 gigapascals, so these are units of pressure, and it has a yield strength of 95 megapascals. The yield strength is the maximum stress the material can withstand before it experiences permanent plastic deformation. Some fixed parameters important to this problem include the spacing between the supports on the left-hand side, that's a ½ meter. The length of the beam is 1 meter, and the applied load is 5,000 newtons or 5 kilonewtons. Here's the problem formulation. We want to minimize mass, the cross-sectional area, times L2, the length of the rod, times the density of the rod material, or aluminum, with respect to the radius of the circular cross-section, and x, the location where we are attaching the rod to the beam. Subject to two constraints. So what's going on here? N sub s, this is a nonlinear function that tells me the safety factor with respect to the yield strength of the material. If n sub s equals 1, then we are right on the edge of yielding. If n sub s is greater than 1, then we are farther away from yielding, but if n sub s is less than 1, then that means we've failed. If we rearrange this from the negative null form, we can realize that we are requiring that the safety factor for yield must be greater than or equal to an allowable safety factor. N sub b is similar. This is a safety factor for buckling. We are requiring that the safety factor for buckling is greater than or equal to an allowable safety factor. In this model, we have some other important elements. The area, the cross-sectional area, is equal to pi times the radius squared. The density of aluminum is 2,800 kilograms per cubic meter. And we also have some bounds. So as I've mentioned, this is a safety factor against yield stress failure, safety factor against rod buckling failure. And here we're going to assume that the allowable safety factor is 1. Just a quick note about terminology here. When we have something in a formulation that says subject to, this usually refers to constraints. These are things that the optimization algorithm is considering explicitly. This is something, if we're, say, using fmin_con, we need to tell fmin_con explicitly what these constraints are. And there actually is a mistake here. These bounds, these should be up in the subject to portion of this formulation. The where statement is different, though. Here we will often find the definition of parameters, models, or other relationships, but these are not usually things that are explicit constraints in the nonlinear programming implementation. So fmin_con is not going to see these where statements directly. However, in evaluating our objective and constraint functions, we may need to be using some of these definitions or relationships. And so these could show up within individual functions in your code, but it's just not something that the optimization algorithm deals with directly. So that's the difference between how we use subject to and where in optimization formulations. Engineering analysis is required for optimization to find the safety factors that we need for the constraints. We can go through using equilibrium conditions and determine what is the axial rod force in terms of known quantities. So we know L1, we know P, we know X, we know H. These are all things that we know. These are things that, given a candidate design, x, and r, we can calculate all of these things. We can now calculate the yield stress safety factor. The yield stress safety factor is going to be equal to the yield strength of the material, that's a material property, divided by the axial stress. The axial stress is equal to the axial force divided by the cross-sectional area. So we invert that, and we end up with Sy times A over the axial force. If we make the substitution for area, then the safety factor is equal to the yield strength times pi r squared over Fr. The critical load for buckling is this formula, which results after we go through and work out what is the area moment of inertia for a circular cross-section. So this is pi cubed times Young's modulus times r to the 4th power divided by 4 times L2 squared. But what is L2? This is not something that we have defined as a fixed parameter, and it's not an optimization variable, but it does depend on other variables. We can define L2 as equal to the square root of h squared plus x squared. The buckling safety factor is a little bit more complicated. This is equal to the critical load for buckling divided by the axial compressive load. And if we go through the algebra, this is what results. This is a fairly nonlinear relationship, but we can see what it depends on. So we have the radius up here and x. The other things up here are fixed parameters. And then down here in the denominator, we have 4 times the load times L1, and h, that's fixed, x, that is a design variable, all to the power of 3/2. So now we have a mapping. We have a way of taking a design that's specified in our design space, in the XR design space, and calculating our objective function and our constraints. This is what I would refer to as a design-appropriate model. As we're developing models, we need to keep a number of things in mind. We need to predict performance metrics as a function of changes in independent design variables. Not all models are going to be able to do this for us. We need to capture in the model the underlying physical mechanisms that pertain to how the system performance changes with design. There's usually a balance that we need to strike between the development effort and computational effort and the accuracy of our models. Sure, we could develop a highly accurate model, but that could take a lot of investment in engineering time to develop the model, or it might also require a large computational effort. Deciding what this balance should be is a challenging decision in an engineering design optimization effort. Are there other model options for this particular case? Let's think about the structure. Well, we made a lot of assumptions. What if we assume that the beam is elastic instead of rigid, and we start to take into account the structural considerations of the beam? What if we have a more realistic representation of the loading, or what if it has dynamic considerations? There are a lot of things that could be going on. What if we look at more detail in the geometry? Are there going to be stress concentrations? These are all things that we could do to improve the accuracy of our model. Let's have a look at these two main failure modes, yield and buckling. For an arbitrary design in our design space, it's difficult for us to predict which one of these modes, failure modes, is going to dominate. These are very nonlinear relationships. Here's an important question. How can we quantify which failure mode dominates? And what do we mean by dominate? The failure mode that dominates is going to be the one that is really driving the solution. And using the terminology that we went through before, it's going to be an active constraint. The way I've defined the constraints here, we can say that for a given design, XR, if we evaluate the value of NS and NB, whichever mode has a lower safety factor for a design, that's going to be the dominant failure mode. Or in other words, think of a design, and if we start applying a load, maybe starting at 0 and gradually approaching the 5 kilonewton load, if one of these failure modes, one of these safety factors is less than 1, then we're going to reach failure with respect to the failure mode that has the smallest safety factor. Due to these nonlinear relationships, the failure mode dominance can change in the design space. So maybe NB is greater than NS in some parts of the design space, and the reverse is true in other parts of the design space. This is something that can very easily happen in practical engineering design optimization problems. When we are using optimization, it resolves this issue automatically. We don't have to know which failure mode is dominant if we are applying a nonlinear programming solver that allows for inequality constraints. What does this dominance relationship look like for this structural design problem? I think it's often helpful to visualize things like this so we can get some insight into these trade-offs. If we were to plot both NB and NS as a function of radius and attachment position, this is what we would see. Here is where we're varying x. Here is where we are varying the radius. We have two surfaces shown, and one of these surfaces is the buckling safety factor, and the other surface is the yield strength safety factor. Over in this region, it turns out that the buckling mode is the dominant load. So it's this surface I'm tracing the edge of right here that is underneath the other one. This surface corresponds to the buckling mode. So if I had a design right here, and if I started applying a load, I'm thinking in terms of which surface would I hit first as I move vertically. I would hit the buckling mode surface first. So that's the dominant mode. But if I look over here, the relationship is reversed. There's actually this curve right here where the two surfaces intersect. And if I go on the other side of this curve, then it's the yield stress failure mode that's dominant. So the yield stress failure mode, I'm tracing its outline right here, that is the one that is closer to 0. It's smaller. That's the dominant failure mode. Over here, we have large radius design. So we have a small radius design here. Here we're increasing the radius. Large radius designs, they're going to have high mass. They're not going to be optimal designs. We're trying to minimize mass. For the lightweight designs that we care about, that have a low radius and a small attachment position, buckling is the dominant failure mode. This is a really big observation. This is not something we can always do. It's nice that we only have two design variables, and these are constraints that we can visualize in the design space. And because of this observation, because we can see that at least for the designs we care about, buckling is dominant, then we can make some significant assumptions that help us to simplify the problem even more. We can safely assume that buckling is the dominant failure mode. And with that observation, with that assumption, we can focus on satisfying the buckling constraint. So if we ignore the yield strength constraint, that simplifies the problem. Let's conceptualize this first. Let's suppose we are just assuming a value for radius, and then we're going to see what happens with the other relationships for a fixed value of r. We want to see how the buckling safety factor and the axial force change with x. With this visualization, can we observe whether there is a design sweet spot? Here I've plotted as a function of x, attachment position, for a fixed value of radius, 1.2 centimeters. several different quantities. The black line, that is the buckling load safety factor. And we can see how that increases and then it decreases. And that is quantified over here on the right-hand axis. And then on the left-hand axis, we have the axial rod force, and that is quantified using the blue line. We can see that with a small attachment position, this force is quite large, and then it decreases, which is expected. And this red line, this tells us what the critical load is for the rod. And this depends on geometry and on the stiffness of the material. But that's not changing in this design problem. As we increase the attachment position, we are increasing the length, and that is going to reduce the critical load. We want to make sure that the compressive force does not exceed the critical load, and we can see that occurs right here. The safety factor for buckling initially increases with x, because as we're increasing x, we are reducing the axial force. And this is a really steep drop-off with the blue line. So it's pretty easy to see how that is going to be the dominant factor in this region. But eventually, as we move to larger values of x, the buckling safety factor decreases because we're increasing the length. This critical load, it keeps going down, and eventually it goes down low enough that the safety factor for buckling is going back down. Because we have this local maximum here, we can observe that there's some synergy between the axial force and buckling stability. It produces what we could think of as a sweet spot with respect to maximal buckling. If we want to produce a design that is as resistant as possible to buckling, then this is where we want to be. That's not our design objective, though. Remember, we're trying to minimize mass with respect to constraints on buckling and yield. Here, let's recognize what our allowable safety factor is. That's n allow equals 1. So that's this green line, and anything any design where the safety factor is above this green line, that is a feasible design. Here's one way of visualizing the feasible domain. So it's all of these values of x where the buckling safety factor is greater than the allowable safety factor. But of course, this is quantified only for one particular value of radius. But this is helpful to understand the trade-offs and relationships that are at play in this problem. What values of x for this given radius will give us the minimum mass feasible rod design? So we have to stay in this feasible domain. If we are holding r fixed, then to reduce mass, we need to reduce x, which is going to reduce the length of the rod. So the smallest mass feasible design is going to be right here. What value of x for a given radius will give us the strongest rod design with respect to buckling? That's going to be this green point up here. Let's take another strategy to understand this problem a little bit more deeply. For each value of x, let's assume that buckling is the dominant failure mode. Let's assume that this constraint is active. If we assume that it's active, then it's also going to be tight. It's going to be satisfied with equality. So then we can state that this formula for buckling is going to be equal to n allow, which is equal to 1. And now we can use this relationship to solve for unknowns. We're assuming that we're right at the limit of failing due to buckling. If we were not at this limit, then mass could be reduced further, and it would not be an optimal design with respect to mass. Here, if we assume this equality relationship, it allows us to solve for r. And if we solve for r, this will give us the minimum mass rod for a given value of x. We can see the x shows up right here, and it also is an input in calculating what L2 is. We can plot mass as a function of x, assuming this optimal R relationship, and find the design sweet spot where mass is minimized. So here we're looking at the entire design space, both R and X, but we've made this assumption that the buckling constraint is active, and so that allows us to define this relationship for the optimal R, and with that, this reduces the problem to something that's even easier to solve. It becomes an unconstrained optimization formulation. We want to minimize the mass with respect to x, but notice we no longer have subject to statements other than the bounds that should be subject to statements. Here we have a definition of what A is. Here's the main difference. We have this relationship for R, and if we have R as a function of x, then we can get the area, and L2, that's also a function of x. So we have everything we need to solve this as an unconstrained optimization problem. Of course, it's not always possible to boil down a problem to a simple one-dimensional optimization problem, but there are a lot of things we can learn here. It requires a number of things, including perceptive observations. It took a lot of creative reformulation, but it also required a lot of modeling effort and design assumptions. We made lots of assumptions. With these simplifying assumptions, we should be asking this question: how far from reality is the optimal design going to be? Or thinking back to the problem formulation decision space, how far away from the origin, the ideal formulation, are we? This may be a good starting point for a structural optimization problem, but we probably will want to improve it if it's something that's going to be informing an actual engineering design. The main purpose of this example, however, is to understand the really interesting trade-offs between the conflicting phenomena and get a sense of the kind of problem that is non-trivial, where it really does make sense to use engineering design optimization as a tool. Let's have a look at Matlab now. We're going to switch over to Matlab. We're going to go through some code that is up on the course website. If you go to the lecture example code and go to ROD design, you can download this code. If you download this code, there are 4 M files. We also have a PDF that goes through in detail the derivation of the relationships. This may be especially helpful if you don't have a background in solid mechanics or structural analysis. This goes through in more detail than we did in the slides, and also discusses concepts such as constraint dominance. If I open the dominance trade-off M file, we can have a look at how this works. We're going to plot the safety factors both for axial stress and buckling. And to do that, we're using a function that I defined called ROD. And this is the main analysis function. Here we are inputting both design variables, x and r. Here we have all the fixed parameters. And then we are just stepping through one piece at a time, where we first calculate what is L2, what's the axial rod force, what's the critical buckling load. Then we can calculate the buckling safety factor. Then if we calculate the area, we can get the stress and the stress safety factor. Back up here, we are returning a number of different output arguments. We have first the buckling safety factor, the critical load, the axial force, the axial stress, and the stress safety factor. So that's what ROD does. If we go back here to the dominance trade-off script, we can see how we're using that. If I'm calling ROD, it's going to only be plotting or using the first output argument, and that is the buckling safety factor. But then here I'm calling N stress. This is the yield stress safety factor. And I define this function that simply calls rod, obtains what the safety factor is, and then returns the safety factor as the single output argument. And that's helpful for this plotting. Here we define what are the upper and lower bounds for the plots, add some labels, and then we can plot this other trade-off as well, where we are holding the radius fixed at 1.2 centimeters, and then we're making some adjustments to the formatting of the plot. So if I click Run, we get both of these figures that we saw earlier in the slide, and I like looking at this one in particular live in 3D. As I rotate it around, it's a little bit easier for me to see which surface is above and which surface is below, and it may be a little bit easier to see where exactly that line of intersection is. So up and to the left, this is where the yield failure mode dominates, and then down here, this is where the buckling failure mode dominates. Then we can go back to this figure, and we've already discussed the elements of this plot. Let's go back over to the editor, and we've already looked at these two functions. Let's have a look at what I've called unconstrained. This is where we have converted, or we've taken the problem that was converted to an unconstrained optimization problem, and we're just visualizing the objective function. We're not actually solving it numerically using something like fmin-unc, but we're taking this relationship and just verifying that yes, there is an interior optimum. Here we go through, define all the problem parameters. We define the space over which we're plotting. And here I'm defining as anonymous functions several things. I'm starting off with L2, which is a function of x, and then r, that's also a function of x, and it's a function of L2, but we define that right there. And then we have the area, that's a function of r, which is a function of x, and then the mass, which is a function of area, L2, and rho, the density. This is what we are after. We want to plot the function, we want to plot the mass as a function of x. So let's run and plot this and see what happens. We're wanting to minimize mass, and here we've varied the horizontal attachment location from a very small value all the way up to 1, and we can really see the effects of the competing phenomena here. So we have some things going on at the smaller values of x, that as we start to increase x, it allows us to reduce the mass. As we increase x, it allows us to change r and still not fail due to buckling. But as we start to increase x even more, then buckling becomes a bigger issue. The critical load starts to go down. And so because the critical load starts to go down, we have to start to increase the radius even more, and that increases the mass. So there is a sweet spot right here. It looks like pretty close to 0.25 meters. That's going to give us the minimum mass. And we can zoom in and see what that result is. And of course, we could get a precise solution using an algorithm such as fmin-unc. Okay, this wraps up this discussion of well-posed, non-trivial optimization problems. There's still a number of topics related to this that are important to go through, including a deeper treatment of monotonicity analysis and other formulation and problem analysis topics. Thank you.